I'd like to talk about the idea that biofuels done right are a good idea, and actually something we likely have to do, but acknowledge some of the challenges and point to some of the solutions in the area of both technology and land use considerations. I hope that the details about biofuels are interesting to you, but I would also comment up front that I believe many of the aspects of making the biofuel situation work are actually, there's some general messages here, and so you might think about what those are as well. I'm going to try to give you a sense of the dimensionality of the issues. I'm not going to try or be able to give you a sense of all of the details. Why do I do this? I've been at it for all of my professional life. Simply speaking, the notion of service and trying to help the world be a better place. This has included 30-year involvement in academic research. I'm a vice president of a large research center on biomass energy. I pay a lot of attention to the big picture issues in terms of resources and environment. I co-led a project called The Role of Biomass in America's Energy Future, and I will be leaving here for the Netherlands for the first Continental Congress of the Global Sustainable Bioenergy Project, and finally Mascoma Corporation, which I'll talk about a little bit more later. So, you know, coming at this from a lot of sides, and if there's something I'm going to be able to offer the world, this is going to be it. So, biofuels done right are a good idea and something we very likely need. You know, there have only been two major resource revolutions in all of human history. Most of human society went from hunting and gathering to pre-industrial agriculture. It's not always called that, but could quite legitimately be called the agricultural revolution. Then, most of society went from pre-industrial agriculture to a pre-sustainable industrial situation, the Industrial Revolution. There are many, many indications, as the previous speaker alluded to, that we have in our century that we live in now to accomplish the third in all of human history, resource revolution. And whereas the first one there were 50 million people on Earth, and the second one there were 750, there are 7 billion now, the first one occurred over millennia, the several centuries, and we probably have to get this one done in less than a century. Furthermore, the scale of societal integration was more small groups early on than farms and villages and cities and countries. When we look at how pervasive the recent economic collapse and near collapse was, we realize we live in a highly integrated world. Essentially, the human enterprise has one experiment to get it right, not many parallel experiments, only some of which need to succeed. So basically, compared to the other transitions, we have more people, less time, and higher risk. And I truly believe this should be regarded as the defining challenge of our time. So, if we imagine a sustainable world, we have some human needs to meet. We have a fairly finite source of potentially sustainable resources to meet those needs. Most of the paths from the resource side to the need side go through one of two things, either photosynthesis, plant biomass, or sustainable electricity. We can add some secondary intermediates. We have some choices. These are boxes that multiple arrows go into or out of. We also have some sole supply relationships. Essentially, you have to start in one and only one box to get to another box. So in the case of biomass, this is the only foreseeable sustainable source of food, organic materials, and organic chemicals. Now, there's a lot of different kinds of biomass out there, and a lot of different metrics you can evaluate them on, so-called first generation, the things we deploy now, second generation, the things we don't yet deploy but hope to. You can look at the properties of the raw materials. You can look at sustainability and environmental metrics. You can look at processing costs with current technology. And I think three things to take away from this detail are, one, that sugarcane, as grown in Brazil and other warm parts of the world, is the most meritorious of first-generation feedstocks from a broad array of metrics, but the range is restricted. Cellulosic biomass, and I'll define what that is, essentially the structural part of plant matter, is the focus of all studies that foresee very large-scale, widespread biofuel production. And algae has some distinctive and attractive features and is certainly worthy of study. But the potential for algal production at a cost per unit energy less than foreseeable petroleum prices has not been described even prospectively and is therefore very much in doubt. So we should look at that, but it's certainly hard to count on. In terms of land productivity, I don't think we think enough about this. How much fuel can you make per unit land? Very, very little with, for example, soy biodiesel, which I actually don't think makes any sense. Not a great deal more with corn ethanol, which is what we do now, which I don't think makes a great deal of sense either. Potentially much more with cellulosic materials. But the actual underlying insight here is really very simple. If you want to grow a lot of plants on a unit acre, first of all, harvest the whole plant. And secondly, grow plants that are optimized for photosynthesis rather than that are optimized to produce stuff that doesn't help harvest sunlight, like starch, oil, or sugar. Interestingly, we buy energy in a broad array of units. And they're somewhat difficult to compare, obviously. We get oil per barrel, we get natural gas per standard cubic foot, we get coal per ton. But it's not a difficult exercise to put them all on a common set of units, like dollars per gigajoule. And a couple of messages there. You see that coal is a very inexpensive source of a gigajoule, or a BTU, if you will, but very inexpensive. I think I said that right, but if I didn't, I'll correct it. Less so if we have to worry about the carbon, but still, frankly, on the low end. I revise this slide from time to time. Oil's been all up and down, as you can imagine. Interestingly, cellulosic materials are about $4 a gigajoule, and this is competitive with oil at about $23 per barrel oil, just in terms of purchasing the energy itself. When I say cellulosic biomass, I'm talking about stuff like wood chips, grasses, waste bagasse, agave, which can grow in very dry climates at high productivity, and also waste materials such as waste paper sludge, which now goes to the landfill. Another driver for biofuels is climate. You know, fundamentally, photosynthesis consumes CO2 to make plant matter. The cycle starts with consuming CO2. If you then convert the plant matter to fuel and use the fuel and burn it in your car, you have the potential for a sustainable carbon cycle. If you manage what's going on in the soil, you actually have the potential for a negative carbon cycle for a period of time. That is negative net emissions or net removal of CO2 from the atmosphere. And that's where you really ought to look at it, because capturing the CO2 out of the tailpipe of an automobile or in any mobile application is something nobody's talking about, and for good reason. You know, there are a lot of different kinds of transportation modes in addition to personal vehicles, and this is schematically representing the idea that there are multiple ways that we could conceivably store energy as we consider our options going forward. Some of them make sense, some of them don't make sense. We probably will and should have a transportation sector with increased electrification. However, I can pretty much promise that the children of anybody alive today will never ride in a battery-powered jet for various fundamental reasons. And heavy-duty applications also are very problematic for electrification. So, for example, even with the ultimate foreseeable electrification, we'll still use over 50% liquid fuels in order to provide transportation energy. The Electric Power Research Institute and Natural Resources Defense Council did a high penetration projection for 2050 for electrification for vehicles, and that provided 28% of transport energy. Hydrogen is something we should look at. Until something starts working a lot better, folks, we need to look at a lot of things. But it faces many challenges, and especially, again, for the heavy-duty sector, and especially if we insist, as we need to, that hydrogen be generated from low-carbon sources. So, although people often talk about biofuels as something that is discretionary and we might choose to use, my view is that without biofuels, achieving a sustainable transportation sector is quite unlikely. The issue of food security and competition with land I'll come back to later, but I heartily recommend to you this book, Enough: Why the World's Poor Starve in an Age of Plenty, written by 2 award-winning Wall Street Journal reporters. And they go through in great detail the reasons for food insecurity and hunger. Poverty is a big one. All of the world's hungry are poor, without exception. Local production being undermined by foreign subsidies is a fact of life. Very poorly developed agricultural infrastructure and degraded land. If you're making biofuels from things you can eat, there are at least some negative and potentially important negative consequences on food security. In particular, other things being equal, if you create an added demand for things you can eat, the price of stuff you can eat is going to go up, and that's not good for the world's hungry and poor. But as you start producing biofuels from things you can't eat, especially on land that you can't grow crops on, you see positive indicators across the board. So there is potential for biofuels to help be an asset in addressing food security. So I could give you a longer version of that, but at least I would invite you to join me in the conclusion that there's a lot of reasons to try to do this, and I want to give you an impression of what's stopping us. Essentially two things. One is, it's a bit of an awkward phrase, but the recalcitrance of cellulosic biomass. It's difficult. In fact, we don't fully know how to overcome this recalcitrance, to produce something reactive. Sugars would be one example, but to produce something reactive from cellulosic biomass with high efficiency and low cost. And the other widespread concern, although I think there are answers to it, is, yeah, but how do we reconcile the land this will take with all the other things we want to do? In terms of the recalcitrance, as I mentioned, you can think of processing cellulosic biomass, the stuff we can get for $23 a barrel oil, first into intermediates such as sugars. That's most promisingly done by cellulase enzymes. And so this first step, we actually know a lot about the second step globally. We produce 20 billion gallons of fuel from sugars in Brazil and the United States. This first bit is the most costly. It has the greatest potential for R&D-driven reduction, and it's generically enabling and indeed sufficient if we can figure that out. The big problem is that this enzyme costs too much. Industry represents it's not $50, my goodness, 50 cents to $1 per gallon of ethanol, and so the cost of the catalyst actually approaches the cost of the raw material. If you know anything about the economics of commodity businesses, and oil refining being the quintessential example, that's not on. This is unacceptable for a commodity product. Well, there's 4 biologically mediated events that need to happen in the course of biologically making a fuel, and as we look towards the future, we can anticipate combining those events into a single process step. This is referred to as consolidated bioprocessing, or CBP, and it's widely considered to be the ultimate low-cost configuration. It would be a transformative breakthrough for any fuel molecule, and Mascoma Corporation has bet the farm on this idea. My background is not business, but I'm intimately involved in this company, and I'm struck that that's really the role of startup companies, is to bet the farm on something, and so it's exciting. But finally, where's this raw material going to come from? Could we make enough biofuels in order to respond to the mega challenges, not just make a good business, but actually respond to energy sustainability, energy security, these big issues? Well, there are factors that make meeting this more difficult, which we need to acknowledge. There are also some that make it easier. And so the plot here is essentially multiples of what we do now. And this is for the US. It's a very important question globally. I'm involved with a large group of people trying to address this globally, but for now, that's a big undertaking, which we're tackling. So people driving more per person makes this tougher. Population going up makes it tougher. There are some factors that potentially make this easier, but then if we start thinking, okay, we actually got to the vehicles we have now and their efficiency in a relatively energy unconstrained environment, if there's one thing I'd like to leave you with in general, it's the idea we will not solve, I've been studying this issue all my life, we will not bring the world to a modern standard of living only with new energy supply. We simply must use energy resources more efficiently. And so, consistent with that, we could have the demand pie by driving more efficient vehicles. And as we look at the raw material supply, that's something we haven't looked at very hard, we being the research community. And so the message here is that there's at least, and this is a very live issue right now. Again, I'm going to a conference to begin a major international process on this, which is why, regrettably, I won't be here through the evening and tomorrow. But my overall sense is that the number and magnitude of the solutions exceeds the number and magnitude of the factors that make this more difficult. I want to close with this last slide to give you a sense of what a solution might look like, but also to underscore the general message that Innovation and change has got to be part of the future, and when you hear that something can't happen, it's usually because people are assuming we won't or can't innovate and change. So here's the land required for current U.S. mobility, about 1 billion acres at a status quo scenario, but advanced processing would lower that. Vehicle efficiency, and frankly, we're not serious about this if we're not prepared to use resources more efficiently. We haven't worked very hard on biomass yield, and then there are multiple ways to integrate biomass production for energy into the landscape without compromising food production, and I believe it's actually a very realistic goal to meet the United States transportation energy requirements from biofuels using currently managed land and therefore recruiting no new land into production. So I would be delighted to follow up with anybody who has an interest at the break or lunch or what have you, and I thank you for your attention.